Hello there, Mr. Sutton bringing you the BC Calculus 8-4 Extra Practice number 6 solutions on vector free response practice. For this no calculator free response, we have a moving particle given parametrically by x of t comma y of t. They're telling us at time 1 we have the point 2 comma 6, and here's our velocity vector for all positive times. First task is to find the acceleration vector at time 3. So let me start by rewriting my velocity vector here. So I'm going to explicitly write out that x prime of t is this thing, and while I'm at it, I'm going to rewrite this as 1 minus t to the negative 2. And now I'm also going to write that y prime of t equals 2 plus t to the negative 2. So this does a couple things. Rewriting it like this makes it easier to take the derivative, which I'm about to do because acceleration is x double prime of t comma y double prime of t. It also just allows me to explicitly say, you know, when I'm using my my x component of my velocity, now I can just refer to that as x prime, and people know exactly what I'm talking about. I could probably say x prime and people would know I meant this thing here, at least if they were grading this on the AP test, but it's nice to have this just kind of spelled out so there's no question about what I mean when I say x prime. Alright, so now we have to actually take these derivatives algebraically and then plug 3 into them. And I have to actually show the algebra here because I'm not allowed to use a calculator on this one, so I need to show what I'm plugging 3 into. So let's see here. This derivative is going to come out to 2t to the negative 3, just using my power rule. And for y prime derivative, so y double prime, that's going to be negative 2t to the negative 3. So there's my general acceleration vector. Now I have to actually plug 3 into each of these. So plugging 3 into this first one, that's going to be 2 times, or 2, I guess I could call this 2 over 3 to the third, so 2 over 27, if I wanted to be fancy and put it into something that, you know, resembles an actual number. And this next one then is just going to be negative 2 over 27. So there's my acceleration vector. For this part, we want the position of our particle at time 3. So we're going to have to find the x and the y separately. Each of these I'm just going to use the fundamental theorem. So for x of 3, we have our initial x value of 2, plus, now I need to do the integral from 1 to 3, because I started at time 1 and I'm going to time 3. Integral from 1 to 3 of x prime of t dt, the change in x. So let's see here, we've got 2 plus the antiderivative of this thing evaluated from 1 to 3. So antiderivative of 1 is just going to be t. So we have a 2 plus now evaluation box here, t. And then this was initially minus t to the negative 2. That bumps up to an exponent of negative 1. Dividing by negative 1, we actually have plus t to the negative 1. And all that evaluated from 1 to 3. So I've got 2 plus all this stuff with 3 plugged in. So that's going to be 3 plus 1/3. And now we have to subtract all this stuff with 1 plugged in, so minus, and then we have a 1 plus 1 over 1. No need to simplify, but if we did, it's worth noting that we have a 2 here and a negative 2 for this second bracket. Those are going to cancel, so we really just end up with 3 plus 1/3, which is 9/3 plus 1/3, so 10/3. So there's our x value. Now we want to find the y value also at time 3. Y of 3 is going to equal the y value at time 1, which was 6, plus the integral from 1 to 3 of y prime of t dt. So we've got 6 plus, and now the antiderivative of the y prime here, that's going to be 2t. And then this is going to be, let's see, this was initially t to the negative 2, bumps up to a negative 1, so we have minus t to the negative 1, evaluated from 1 to 3. So we've got 6 plus this stuff with 3 plugged in, minus this stuff with 1 plugged in. So altogether, let's see here. If you wanted to simplify it, we've got 6 plus another 6 is 12. I'll worry about that minus 1/3 later. We've got, let's see here, this is all 1 inside here that we're subtracting. So that's going to be 11 minus 1/3 when all is said and done, which you could call 33/3 minus 1/3, or just simply 32/3. So our point at the end of all this is going to be 10/3, 32/3. For this part, we want to know for what positive time does the line tangent to the path of our particle have a slope of 8. So we're going to come up with an expression to represent the slope of the tangent line, and then we're going to set it equal to 8 and solve. So we're basically looking to see where dy over dx equals 8. Well, if you're talking parametrics, dy over dx is really the same as y prime of t over x prime of t. So let me actually write out what those are, because I'm going to have to solve this at some point. So y prime again was this 2 plus 1 over t squared. X prime was 1 minus 1 over t squared. So this basic setup. Now we want to figure out at what time value, what value of t, this whole thing equals 8. So to solve that, let me start by multiplying both sides by this 1 minus 1 over t squared business. That's going to be 8 minus 8 over t squared on the right side. And now let's see here. I can multiply everything by t squared to get rid of those denominators. So that's 2t squared plus 1 equals 8t squared minus 8. And just moving things around now, I can have, let's move this 2t squared over here. So we have 6t squared on the right and 9 on the left if I add that 8 over there. And now if I divide by 6, that's really 9 over 6, which is going to be 3/2. And then I just need to take the square root of that. I'm not going to write plus or minus because they said time was positive. So we really just have a positive then, positive radical 3 over 2 for our time. For this last part, they're telling us our particle approaches a line as t approaches infinity. They want the slope of the line. So to get this, we essentially need to figure out the limit as time approaches infinity of dy over dx, which is to say the y prime here over the x prime that we were given. So we already wrote this setup in part C. The only difference now is that instead of setting this equal to 8, we're finding the limit as t approaches infinity of this expression. So as t approaches infinity, these bottom heavy fraction parts here are going to go to 0. So you really just have 2 plus 0 over 1 minus 0, or just simply 2 over 1, or just simply 2. So that's the slope of the line that we're approaching as time approaches infinity. For this calculator-based problem, we have a particle moving in the xy plane with x of t comma y of t given as the position of this thing. And they didn't really tell us what those meant algebraically, but they did give us x prime and y prime down here. They also told us at time 1 the object was at the position 2 comma negative 3. So our next task here, our first task rather, is to find the equation of our tangent line for this curve at the position 2 comma negative 3. Well, for a tangent line equation, you need an x value and a y value, which they gave us, and you also need the slope. So to find the dy over dx, which is the kind of slope we need, to find that at the point 2 comma negative 3, I need to do the y prime and x prime at time equals 1. So y prime of 1 over x prime of 1. Now the good news is I already know what y prime and x prime are. They gave those to us up here. So I'm just going to do this piece on the calculator now. To make my life a whole lot easier on this part of the problem and really the rest of it, I'm going to enter both of these in my y equals. So here I am in the y equals. For y1, this is the x prime basically, t of e to the negative t. And notice I'm using x instead of t because that's the input variable on my calculator. And now for y2, this is actually my y prime. Now they gave us secant of e to the negative t. To actually input that, you need to do cosine of all that stuff and then raise that to the -1 power because secant is really the reciprocal of cosine. So now that I've got that entered in there, let me just do y prime of 1 over x prime of 1. So I'll just do a fancy fraction here. For y prime of 1, I do alpha trace y2, because that's where I stored y prime, and I plug 1 into that. And then down below, for x prime of 1, I do alpha trace y1, and plug 1 into that as well. Press enter, and that's about 2.7806 or 781, depending on how far you want to round that out. So now to get the equation of my tangent line, I'm going to have y minus the y value negative 3, so y plus 3, equals my slope of 2.781, which seems awfully close to the value of e, at times x minus the x value of 2. For this part, I want the acceleration vector and speed of the object at time 1. So for the acceleration vector, I need x double prime of 1 comma y double prime of 1. Now the good news is I've already got x prime and y prime defined up here, so I can just take the derivatives of each of those at 1 on the calculator without showing any further work. Let me go ahead and do that. So to start things off here, I'm going to do math 8 to get my derivative. I'm going to do dx, and then if I want the derivative of x prime to get x double prime, I'm going to do alpha trace y1, because that's where I stored x prime. And I'm doing this at the input value of 1. And now press enter. That's about negative 0.4223. There we go. Let me do the same to get y double prime of 1 now. So I'm going to yank my input from before. The only thing I'm changing is I want to take the derivative of y prime to get y double prime. So I need the derivative of alpha trace y2 this time around. Everything else is the same though. And that comes out to negative 0.152. Next, to get the speed of the object at time 1, I need the square root of x prime of 1 squared plus y prime of 1 squared. So plug in all that into the calculator. Here we go, square root, and I'll just do the rest of this off camera. So here's what the rest of this looks like. We had alpha trace y1 of 1 squared plus alpha trace y2 plug in 1 squared. Press enter, and that's about 1.139. Now notice that they didn't give us any units in this problem, so we're not going to give them any units back. For part C, we want the total distance traveled by our object on the interval from 1 to 2. So for this, I'm going to need the integral from 1 to 2 of basically the speed function. So square root of x prime of t squared plus y prime of t squared dt for my differential. And since x prime and y prime are already defined up here, I can just plug this whole thing into the calculator. So here's what the setup on my calculator looks like. Integral from 1 to 2, square root of, and x prime squared is really y1 squared on my calculator. Y prime squared is really y2 squared. And we use an x instead of a t. Our calculator figures it out because we did everything in terms of x. That does the same thing as t is going to do down here. So pressing enter, total distance is going to be 1.059. For the final boss battle on this one, we want to know if there is a time greater than or equal to 0 at which our object is on the y-axis. Explain why or why not. So to figure out the whole y-axis business, we're basically asking about the x function, x of t. We want to know if there's any time at which x of t could equal 0. Okay, well, let's talk about what x of t is at time 0. Let's at least see where we're starting here. And then if we can take a look at the slope, or the rate of change of x of t over time, based on where we're starting, those two pieces of information will tell us if it's possible for us to get a value of 0 out of x of t. So x of 0, because they didn't give us time 0, they gave us time 1 here, x of 0 is going to be my initial x value of 2 plus the integral from 1 to 0 of x prime of t dt. So let me do that on the calculator. So recall that I stored x prime as y1, so I'm doing 2 plus integral from 1 to 0 of y1, alpha trace y1, and that comes out to 1.224 and some change there. So we're starting to the right of the y-axis. Now let's take a look at the slope. So for times greater than 0, and by the way, this is positive here. So for times greater than 0, what's happening with our slope? Well, that's governed by this dx over dt function. So we're taking the tan of something. Now let's take a look at what we're taking the tan of here. For time greater than or equal to 0, this e to the negative t function, e to the 0 to the negative 0 basically is 1, and then this thing just keeps decreasing from there, but it never gets below 0, right? There's a horizontal asymptote for exponential functions on the x-axis. So that means that this e to the negative t part is always going to be between 0 and 1, or actually a little bit more than 0, between 0 and 1, as long as your t values are positive. So what that means is you're always taking the tangent of something between 0 and 1, not including 0. Well, tangent is positive for a while, right? It's positive at least up until pi over 2, which is more than 1. So that means that this whole expression, dx over dt, tan of e to the negative t, is going to be greater than 0 for all t values that are greater than or equal to 0. So basically, your particle starts to the right of the y-axis, and based off of the derivative of x, our particle is always moving to the right as well. If you're starting to the right of the y-axis and always moving right, you're never going to get back to the y-axis, so you're never going to touch the y-axis based off of this.